Really good to be in that panel, really good to be among all these interested people. I wanted to talk a bit more about our outcome-centric way at DSV. This is something that we've been developing over around 7 years, 7 generations of founders, and this is the best that we've seen in terms of scoping. So why even do that? Why do we take a design approach to venture science? So currently the status quo in science commercialization is that we do scientific research, we make discoveries, and then sometimes scientists, researchers work with tech transfer officials, professionals, and they interrogate or evaluate the utility of those applications. And this is what is commonly referred as tech push. However, focusing on the how technology solves a particular problem is limiting to many other technologies and many other solutions that we can be taking to solve the same problem. And also for all the applications, there may be a combination of different technologies that can be combined in many different ways, which means that the space of combinatorial innovation is really a lot bigger in the case of tech push. So this is why we think it's really important to take a much more design an outcome-centric way and work backwards from the societal outcomes that we want to achieve to identify the ideal solutions and ways of achieving those. And also this is quite important in the context of building ventures, because by doing that, we can select the specific technical components that have a risk, that they're sufficiently de-risked and individually to a great extent. So today I will be covering DSV's scoping ontology, scoping language, how we bring this all together. I'll be giving examples. The scoping language at DSV sits at the core of how we build ventures. It helps us work backwards from outcomes. And by outcomes here, I mean well-formed statements that describe an ambitious action that we want to take to reach a future state. And that future state is a world that is greener, healthier, more regenerative, more equitable, and so on. Using that language, we can also reason about the known constraints, and this can be technical and commercial, and also helps us reason about the possibility of different solutions to these constraints and how important they are. And having done that, we can also describe the kinds of experts that we need to come together and hold those pieces of knowledge and take those solutions to market. And importantly, helps us collaborate more. So having a common ground to talk about things helps people across domains to speak the same language. I also wanted to situate a little bit outcomes graph, or like outcome-centric approach to different schools of thought that we've experimented with or have inspired us in many different ways. I bet you're familiar with knowledge graphs. These are big maps of what we know about the world. They're great at mapping existing pieces of knowledge, allocating gaps in a networked way. However, they don't tell us much about the applications of that knowledge. Another kind of school of thought are technology roadmaps. They're really good for, in a milestone way, presenting different technical milestones that need to be achieved for the final technical products to be developed. However, they're really technocentric. They're not outcome-centered. Usually they're static and they don't classify, for example, those outcomes based on what it takes to move them through stages. Another approach that has inspired us quite a lot, developed by Joel Chan, is called discourse graphs. This is a protocol and a way of representing arguments and claims and evidence about the applications of science in society. And it helps us also capture the creative exhausts of our scoping efforts. However, they're a lot more focused in academia. So we're capturing claims and evidence and hypotheses in an academic paper, but they need a lot more to be transformed into something that can be used in venture. And the last set of ideas that has inspired us is the sensitivity intervention and tipping point analysis, because we want to be able to reason and intervene in sensitive points in an ecosystem and change whole sectors. So the tipping point analysis really facilitates the path of least resistance analysis, but to our knowledge has been mostly being used in policy. So we've taken bits from all these approaches, and we've developed our own ontology, a language that we use to describe different primitives. Just to recap, scoping is a process by which we work backwards from a desired outcome to improve our understanding, and that is how complete is our scoping of all the possible ways that we can achieve that outcome, how possible we believe different outcomes are today. So based on completeness and possibility, we refer to solutions. And these are things that we believe today are possible. Like, for example, today it is possible to use bacteria to break down the tumor microenvironment. Solutions can also be other companies that have a proven impact on the outcome that we care about. When our completeness or our scoping is not so full, we refer to hypothesized solutions, and these are things that might be possible today. These can be promising future directions that we want to take that can become solutions the more we increase our confidence in them, or it can be flipped constraints and so on. And another last category in the higher possibility nodes, quote unquote, is tactics. And these are used sometimes to signify some general directions that we may take. Usually they're not as precise or quantified as a solution. Like, for example, we may say that in neuroinflammation in pharma, we may use different kinds of immune cells like microglia or whatever that is, but we are not making them as precise. But we can increase our confidence and make them solutions later down the line. On the lower possibility side, as in items that block our pathway toward achieving the outcome, we have constraints. And these are outcomes that we believe today are not possible, something that blocks us. And typically that can be a challenge, a bottleneck, something that sits at the root cause, like a thermodynamic limit that does not allow us to proceed. We also refer to hypothesized constraints. And these are outcomes that we believe today might not be possible. This can include failed attempts to apply a specific approach to an outcome. It can include assumptions about the status quo that are held by other founders, by investors, by incumbents. It can also be that we don't know the possibility of that outcome because no one has attempted to apply this capability to the outcome. And lastly, on the lower possibility side, we frequently use requirements. And by that, we mean we want to signify something that has to be true for a solution to work. That is usually requires further specification or is very vague, is a generalization. Like, for example, we may say something like all cell and gene therapies must not induce immune reactions, or they must be easy to manufacture. Or like in agriculture, we may say something like any post-harvest facility needs to be relatively close to the farm and so on. And we do collect those requirements early on, and as we increase our confidence, we make them more precise and they move up the ladder to become hypothesized constraints or constraint. So this is these are kind of the building blocks of our scoping ontology. And you may be wondering how it all comes together. And I thought I would just bring this alive using examples from our climate team. This is an illustration of what I'm going to cover next. So usually we start by understanding the high level state of the art. So we map key concepts and key ideas in the field. And importantly, we characterize top level outcomes. So in that case, it's avoiding all greenhouse gas emissions and also removing all excess greenhouse gas emissions. At that level, we are trying to break the problem down into mutually exclusive categories and also collectively exhaustive as much as is possible. And importantly, we want to be really ambitious. So here you can see a constraint that, for example, today is not possible to permanently remove up to 20 gigatons of CO2 by 2050. And it's really important that we constantly push and prompt our founders to be ambitious at that level, because it's much harder to re-ambitionize our approach later down the line. And then when we dive into the prevailing market dynamics and business models, and then we find some requirements that our optimal solution is to fulfill. So in the case of negative emissions technologies, we need the carbon removed to cost $100 per ton. We want to be able to sequester 1 gigaton. We want to store it for 1,000 years, so it needs to be permanent. And we also don't want to mess up with different environmental ecosystems. And it's quite important to collect those requirements and be precise. And we become a lot more precise later down the line, because this helps us prune and clean up and prioritize subsequent approaches. And then this is the same kind of outcome that I was just showing in the previous screen. But we also obviously map different tactics, like different ways of achieving those outcomes. So in the case of negative emissions technologies, we may use abiotic negative emissions, and these are things like leveraging geochemical pathways, like enhancing the weathering rate of rocks, or we may use artificial negative emissions. And these are, you may have heard of direct air capture. There are electrochemical ways by which we can suck out carbon from the air. And within those, obviously, we have a lot more details. Just some examples that our founders have been working on, like the bits in blue. And each of those has its own set of sub-requirements, which you can see implied by the little yellow dots on their left. So when we have done solid scoping at the requirement and tactic level, then we seek more evidence in order to start formulating hypothesized constraints and hypothesized solutions. And by evidence here, I mean, it can take the form of reading academic papers and reports and doing market research and IP research, or we also talk to other founders, we talk to advisors and academics. So it takes a lot of different forms. So for example, in the case of abiotic negative emissions, this is work done by Dr. Kate Murphy. She's one of our founders. She was looking at direct ocean capture. So how can you make the ocean draw down carbon? Currently, this has several constraints as an approach. Like, for example, it's difficult to measure the carbon flux across the ocean. Also, it has when you put things in the ocean, it has an increased risk of negative side effects and unknown risks to delicate interconnected environments. So we do that. This is also an illustration, like in reality, that work is a lot broader and a lot deeper, but this is just to show how it unfolded. But at that level, we also start creating relationships and connect and compare these approaches to identify opportunities. A really important part is we constantly prompt ourselves and our founders to flip those constraints and think creatively. So for example, here in the case of direct ocean capture and changing the alkalinity of the ocean, Kate asked, okay, what if I don't need one of the main requirements of that approach? What if we don't need the ocean? What if we can find safe water bodies on Earth and make those carbon sinks? Which led to a hypothesized solution that it might be possible to capture and store CO2 in open pit mine lakes. And Kate, I mean, this representing in this diagram work of several months. So through really detailed analysis, we ended up creating a company called Aquari, which fulfills the requirements of measurability. So effectively is using flooded open pit mine lakes to capture and store CO2. Those pit mine lakes are contained, so we can measure how much carbon we remove. There are no ecosystem risks because there is no life in those acidic lakes. The costs are really low compared to doing that in the ocean. And also there are no limitations around permits and regulations. So hopefully you can see how we use the requirements we set at the beginning to inform the final solution that we went for. This is another example from, again, from the climate team at the same negative emissions technology branch. This is work done by Harry McPherson. He's one of our founders working on artificial negative emissions. The top level constraint that we face there is that it's currently not possible to remove up to 20 gigatons of CO2 per year by 2050 using direct air capture. And something that we've seen quite a lot across our scoping is a lot of first principles thinking. People ask recursively in lots of different depths, like why? Why isn't that possible? You know, what are the critical bottlenecks in current direct air capture systems? So for example, currently lots of DAC systems depend on critical materials and they need a lot of energy. When we formulate that, we want to then take those bottlenecks into principled statements that the optimal solution needs to have. So in that case, we may say that we want to reduce the dependency on renewable energy, and also an optimal solution needs to have reduced dependency on land. But obviously we don't stop there. We want to be able to quantify, like, how big or how important is that requirement? Can we find evidence about that requirement? And in fact, we can. Like, for example, we know that currently, this is a constraint. It's not possible to reduce the energy consumption of DAC system to a minimum of 600 kilowatt hours per ton of CO2. And then in this case, we want to dive deeper and deeper and use that as a pattern in all our scoping across different sectors. Like, we ask, okay, what are the fundamental reasons for that energy cost? Like, what drives that energy cost? And in that case, what is expensive is the energy needed to regenerate the sorbent, and that is the material that we need to, that absorbs the carbon. We need to heat it up again so it releases the carbon safely. And at that point, we want to do a lot of modeling and techno-economic analysis work to find exactly the metric that we want to optimize for. Like, for example, another constraint at a lower level here is that it's not possible to desorb CO2 at an energy consumption of 520 kilowatt hours per ton. And again, then we ask, okay, how can we resolve that? Why isn't it possible? This is something that constantly our founders are asking. And they're trying to generate different tactics, some ways that they can bypass the constraint. So one way to bypass that constraint is by reducing the temperature requirements for sorbent regeneration. And this is where a lot more creativity comes alive. Like, for example, Harry thought that maybe one way to reduce those energy costs is to find some free energy lying around. And we can use that for DAC. And that gave rise to that hypothesized solution that, well, actually, we might be able to use existing energy gradients, like the waste heat from solar panels. And after lots of modeling and rigorous and analytical work, it came up with the company Calorian, which is about to spin out. So Calorian uses that waste heat from solar modules to deliver directly capture the really low energy, high capture rate, then maybe even capture the water from solar panels. You don't use much land because you integrate those modules in existing solar installations, and you combine electrochemical and thermal regeneration to achieve lower energy. So yeah, hopefully you can see this was a summarized version of like 9 months of work, but hopefully you can see some steps and some reasoning that led to us moving in that direction. This is a summary of the different diagrams that I just showed you, and I'm hoping that you can maybe take that away after this presentation and start thinking and applying that in your own challenges and your own outcomes. Something else that I wanted to discuss, the panelists in the previous panel discussed a lot about talent and skills and what makes a good scoper. And this is quite important for us. It's something that we are thinking a lot, especially around training the next generation of venture scientists. So at minimum, we want them to be very creative and also be really good first principles thinkers. So I wanted to share with you a few patterns, a few prompts, like a few moves that we've seen people do. And we are cataloging them. We're making effectively a pattern language for creativity, first principles thinking. So, for example, some moves that we've seen people use to generate more ideas, some more creative scoping moves are grouping and relancing. So maybe sometimes changing the taxonomy or like the grouping of different sub-outcomes to find different or new groupings. Like, for example, in decarbonizing industrial heat, we want a solution that works well with intermittent renewable sources. So then we started looking, okay, how critical that is for textile and chemicals and kind of different sectors, which led to one part of the grouping. But also, like, the optimal solution needs to provide a really good thermal range up to 2000 degrees Celsius. So this is another way to group our scoping based on process and how much energy it requires, like in refineries and cements and metal-based durables and so on. Another move that we've seen people use is they find analogies, they use analogies. These analogies can be based on an attribute, like a quality, or they use analogies from different fields, or they search for other outcomes in their scoping that have a similar target or similar metrics and kind of use them creatively. Or we also seeing people scaling up outcomes to more universal forms and more universal scope. And they're trying to find a theoretical maximum versus what is currently possible. And this pushes us to think more creatively and in a more ambitious way and start answering the question, okay, what is the difference between the current metric versus kind of the maximum potential of any such kind of outcome? And then on the other hand, we have moves and patterns and prompts that helps us get to first principles faster and more effectively, hopefully. These are things like we constantly do root cause analysis. You may have picked it up from my examples, like asking why recursively really takes us quite deep and trying to understand if there are any assumptions hidden at any level. Other kinds of moves is we're trying to be a lot more precise and find the target metric. And then we play around, what if we double that? What if we change this parameter to see if the outcome would change in a meaningful way? Another example is zooming out and mapping all the different options to see if we've kind of missed any category and so on. But this is just examples. We have a bigger list, and this is something that we definitely will be sharing and training our venture scientists to use, and we want to open that up a lot more to many more people to add and contribute and use, hopefully. I'm reaching towards the end of my presentation. You might be wondering, where are we? There was a comment around note taking. Where do we store all that knowledge? We've experimented with quite a few different systems. One is we have a prototype inside Rome, which is a networked hyperlinked knowledge base. It's like a Wikipedia for outcomes. And we also experimented with a lot more visual ways of mapping that using tools like Miro. But what I'm really excited about, something that we've currently been developing, is we are taking what I just described for the past 20 minutes, and we are trying to train AI systems, large language models, to do that work, and with us and then for us eventually. So we're training, it's called it's a new prototype called Element. We're training large language models to reason like venture scientists, generate different ideas, explore possible pathways concurrently, and then bring that back to us. That can help us make better decisions and find better outcomes to different challenges. So cannot see your faces. I'll stop here. I hope that I gave you the building blocks. I give you an overview of how we do it, how we put it together, and hopefully you'll start using it. If you want any help, please reach out. We'll be very happy to discuss and see how we may work together to keep on developing this. Thank you.
Thank you, Irene. I think you really brought it to life for people, that have no prior knowledge of scoping. People like myself, I think it's really helpful. For those that are technical experts, I think it's been really useful as well. So my takeaways are: this is, correct me if I'm wrong, this is systematic, it's intentional, it's precise, it's discipline or sector agnostic necessarily, it's inherently creative, and it's absolutely totally outcome centric. And I think all of those things, as a STEM undergraduate and as a science PhD, I don't think I ever got taught any of those things.
Absolutely. And I think that's the difference, like the first slide, the first point I made about the current way of tech push and like thinking from technologies first rather than applications and outcomes.
Yeah.
This is something that we definitely, I think it's really worth seeing that praxis develop, the different road mapping efforts, different scoping activities at the level of the PhD, but also at the level of creating new ventures. So yeah, excited about that.
Super, thank you. I think the words like foresighting, horizon scanning, scoping, they're all used really interchangeably. This is definitely scoping that we're talking about. Is that right?
Yes, that's a really good point. We're not doing, I mean, implicitly, we are doing some horizon scanning. Like we are forecasting how the world will be in 5 and 10 years from now, when we are looking at the demand for different minerals, for net zero and so on. So we are doing that in some ways, but this is not the main focus of what we do. Then the question that we're trying to ask is, okay, what should we be doing in the different worlds that will be unfolding in front of us? So yeah, we could be doing maybe a little bit more of horizon scanning, but I think it's implicit quite a lot in what we do.
And how much of all of this thinking, I mean, you say you share a visual and actually it's like a year's worth of work or something to get to that point, but how much of all of this thinking has been developed in-house at Leap Science Ventures, and how much has really been borrowed from other areas and from design thinking, etc.?
Yeah, it's a really good point. We've taken inspiration and we've experimented with other schools of thought. Like, for example, discourse graph has been a really big inspiration for us. We've played with knowledge graphs as a way of structuring and organizing, finding nodes and their relationships. So I think we build in the shoulders of giants. I mean, we brought references and ideas from all those different approaches, but what you see here is developed in-house for the large majority. We've seen our founders really, really closely. We've reviewed evidence on like literature on how we use analogies for invention and discovery. and we're putting all that together, and we've built ventures using that. So in a way, it's also a tested way to build science-based ventures.
Super, thank you. My last query is, how widely adopted is this at Deep Science Ventures? Can you give our audience a sense? Is everybody skilled in it? Will it just be for the venture science doctorates to do, the candidates to do? Or is it across the whole organisation?
Yeah, all of us at the core team, our current founders, currently, just to give a sense of the numbers, we built 35 companies. They have been using a version of that. The most latest that I just presented is being used by at least 15 founders and the rest of the core DSV team. And it would definitely be used by the venture scientists. But I mean, that's why we are doing those webinars. That's why we write about it. We want a lot more people to be reasoning and thinking and fitting into that. So hopefully a lot more people. So if you find it interesting or helpful, let us know.
That's super. Thank you, Aurelie. That's